Alright, well I know a bunch of you are fans of sports ball, so let's do a quick example of that. We'll see if we can't get all the touch goals and end up winning the points. J-Random Troll is playing baseball, he dives head first and he begins to slide. Let's say he's sliding to the right. Now because there's friction, he's ultimately going to slow down. Friction points in the opposite direction of motion, so he'll have an acceleration to the left. Remember, anytime you have acceleration in the opposite direction of motion, that's what slowing down is. Alright, so what we want to figure out is what the magnitude of the force of friction is in newtons, and how far he's going to slide before he finally comes to rest. Let's do this thing. Typically the best way to start is to draw a free body diagram. I've gotten it started. Here's J-Random Troll sliding to the right, and let's see if we can figure out all the forces acting on him. One that you can typically always use if this is taking place on Earth, which baseball games generally do, is the force of gravity. This always points straight downward, and it always equals mass times acceleration. Well, I know J-Random Troll's mass, and the acceleration due to gravity is always 9.81. So after multiplying 90 kilograms times 9.81 meters per second squared, I end up finding the force of gravity to be 882.9 newtons. Awesome. Well, what other forces do we have acting on him? I know he's not accelerating downward into the ground, so there's got to be an upward force pushing on him. That upward force is the normal force, because anytime you're in contact with a surface, you got a normal force from where that surface is pushing on you. Not only that, I know he's slowing down, which means he has an acceleration to the left as he travels to the right. That acceleration is caused by friction, specifically kinetic friction, because he's moving relative to the ground. This is the complete free body diagram. That's about it. Now I need to use it to figure some things out. Well, I know that the total force in the y direction is mass times acceleration in the y direction, and I think it's safe to assume he's not accelerating up or down, so that means his acceleration in the y direction is simply 0. And anything times 0 is 0. So his total force in the y direction is equal to 0 newtons. Well, let me look at all my forces that are pointing in the y direction, or at least have a y component. In this case, it's only the normal force that's upward and gravity that's downward. So let me define which directions are positive and which are negative, and there we go. Now I can look at my forces in the y direction and actually add up each individual one. I know I've got normal force pointing upward, so that'll be positive. I've got a downward force from gravity of 882.9 newtons, so that'll be negative. And I know that altogether it comes to 0. So I can use this to solve for my normal force, which is one of my unknowns, and that simply comes to 0 plus 882.9. That's just 882.9. Well, let me update my free body diagram so that I've got that listed right where I need it. Quick timeout while I have you here. Timeout, because sports. The normal force in this instance is the same as the gravitational force. That will sometimes be the case, but not always. If there was another force in the y direction acting on J-Random, then that normal force would be a little bit different. Okay, let's look in the x direction. Now, this time, I don't expect all the x forces to come to 0, because he is accelerating horizontally. And the only force, actually, that I have in the x direction is the force of kinetic friction. Oh, and that's pointing to the left, so I'm going to slap a little negative in front of that. Well, now I'm stuck. I don't know his acceleration, and I don't know the force of kinetic friction. One thing I do know, however, is that the force of kinetic friction is always equal to the coefficient of kinetic friction times the normal force. Now, from the problem, it states the coefficient of kinetic friction is 0.4. So, that means the coefficient of kinetic friction is replaced with 0.4. The normal force is that 882.9. And now I just multiply them together, and I get the force of kinetic friction. Swanky. And that comes to 353.16 newtons. So I'm just going to update my free body diagram again. And now I've actually solved for the first part of the problem. What is the force of kinetic friction acting on J-Random? That's 353.16 newtons. And now the question he probably cares about, how far will he slide before coming to rest? Will he make it to the base or not? How embarrassing would that be, going for a slide and then just stop short of the base and then get tagged out? So, good thing JRandom knows physics, so he'll be able to solve for this. Well, so far when we're asked for distances, we know of two different equations that can be used for that. The distance equation and the combo equation. So let's see what we got. In the distance equation, I don't know the total distance, I don't know the acceleration, and I don't know the time. Yikes. But I do know his starting velocity, and I can assume his starting position is 0, so that's something. But that's 3 unknowns right there. Here, I know his starting velocity. He comes to rest, so I know his final velocity is 0. I don't know his acceleration, and I don't know his change in distance yet. That's 2 unknowns, but that's better than 3 unknowns, so right now the combo equation is looking a lot better. I'm just going to get rid of the distance equation over here, since I probably won't be using it. Now, I don't know distance, that's what I'm solving for, and I don't know acceleration. So what can I do about that? Ooh, how about this? I know that mass times acceleration in the x direction, which in this case is the only acceleration, is equal to negative force of kinetic friction. And I know the value of force of kinetic friction, and I know his mass. Hot dog. So I can just set up my equation here, solve for my unknown, and then plug in my values. I end up with 353.16 over 90 in the negative direction, which comes to negative 3.924 meters per second squared. That negative simply means to the left, because I declared leftward to be negative, and that makes sense to me. If he's moving to the right and accelerating to the left, he's slowing down. Specifically, he's slowing down at 3.924 meters per second every second. Alrighty. So now I can use this acceleration value in my combo equation over here. According to the problem, the initial velocity is 5.4 meters per second. And his final velocity is just 0, because he comes to rest. So let's head back over to my combo equation, solve for my unknown value, in this case delta d, and that's all that I really need to solve for. I'm looking for the change in distance while the slide is happening. And it comes to the quantity final velocity squared minus initial velocity squared all over twice the acceleration. Now I can plug in my known values and calculate it out. Now, because I have a negative on the top and on the bottom, that negative cancels out and I'm left with a positive number, which is great because that means the change in distance was in the positive direction and that's to the right, and that's what I'd expect. And I got right around 3.7 meters. This kind of makes sense to me, and it seems like a reasonable answer. And so as long as he was 3.7 meters or less when he began his slide, he should make it to the base just fine.